Hello everyone. So this is second tutorial of this course, and so I hope I'm audible, right? And screen is visible also. So this is tutorial 2. Okay, let me start with the recording. Yeah. So this is tutorial 2. And today's date is 31st January. Today's date is 31st January. Okay. So in today's this second tutorial, basically what we will do, we will discuss some problems which may help you to solve the second assignment. And if you have any problem specific till now, you can ask anytime in this during this tutorial sessions, or separately you can mail me in the mail ID ma21d018 smail.iitm.ac.in. You can mail, or you can ask here as well. Okay. So if you have any problem, you can ask. Otherwise, I'll start some problems. And um, today, basically, what we'll do, we'll discuss the basis of a vector space, and another is that if we change the basis, so what will be the conversion matrix regarding those things we'll be discussing. So let's start with a problem. So I hope this is visible right now. Okay. So if as I have said in the previous talk as well, that the theorems whatever we will discuss, those are basically whatever will come during the uh, solving a problem. During solving a problem, I will discuss those things. And otherwise, if we are solving any specific problem, that time I will also discuss some theorems. So let's start with this problem. If you have any problem, you can ask in between anytime. Okay. So, and also if you are not able to understand anything from this problem, still you can ask. So let me start with this problem. So what it says, let what it says, let beta 1 is equals to 1 1 minus 2 4, and beta 2 is equals to 2 1 5 0, beta 3 is equals to 3 2 3 4, and beta 4 is equals to 1 0 7 minus 4. These are the row 1, row 2, row 3, and row 4 of a 4 by 4 matrix S B. Now, now the question is, then which of the following elements belong to the row space of B? So let me start with the fact what is the row space of a matrix. Let let A be m by n matrix, So that means A is a matrix with m number of rows and n number of columns. So now thing is that you can consider the entries in the matrix A is either from real or complex or any field, but for now, for your understanding, you can consider it the element entries are from real or complex only. Okay, so now A be an m cross n matrix, then each let A is equals to Aij. Okay, then, or capital Aij you can write, capital Aij, then A1, then row 1 or row 1, which can be written as row 1, which is equals to A1 1 A1 2 all the way A1 n. So yeah, this is row 1, and in this way what we will get, in this we will get row m, which is equals to A1 am1 am2 all the way am n. So now, so these are the row, basically row of this matrix A. So now, then each of them are entry in the field, whatever the field that n. This is a row vector in of n entries row vector. This is an also element. This is an entry in the field Fn. Okay. Then this row 1 to row m, the subspace generated by then subspace generated by row 1 to row m, this set is called row space of this subspace generated by these are called row space of the matrix A. Okay, so that means what it says, if you take linear combination of those rows and whatever the terms will come, they are in the same subspace, subspace of the rows of the matrix A. Okay, so basically row space of a matrix is the space which is generated by those rows. This is what it is mean by row space. Now there is an important theorem, so I'll state that theorem, and after that I'll try to solve this theorem, and that theorem also discussed in the class. But if you are not able to understand, then you can ask here. I can also discuss again. Otherwise, I'll just only state the theorem. That theorem says that if um, R is an row reduced echelon form that I have discussed in the previous class. Even if you ask, I can again discuss. Otherwise, I'll just mention the theorem says that let R be a non-zero row reduced echelon matrix, then the non-zero rows, then non-zero vectors of R forms a basis for the rows space of R. So as I have said, row space. What is the row space of a matrix that I have said? But basis I have not said. So let me once again say what is the basis of a what is a basis of a vector space. Basis of a vector space. I hope all you know. If even if you don't know, you can ask. I can discuss these things in more detail. So what it says, basis of a vector space. Let V be a vector space over a field F. Okay. So now V be a vector space over a field F. So now then a subspace. Let S be a subset. Let S be a subset of V. Be a subset of V. Then linear span. Then the set LS, which is actually given by summation of Ci alpha I, such that I equals to some n. I belongs to some n. So here Ci are coming from the field, and alpha I are coming from the set S, and n is any natural number, any non-negative natural, positive natural number. Then LS is a subspace of V. If LS is equals to that subspace of V, that subspace can be equals to exactly to the vector space V, then we say the set S spans V. This is called span. This is called the spanning set. Basically, spanned by S. This is called spanned by S. Whenever you have a set of vectors and you take linear combination of all possible linear combination of vectors from that set, that is called the linear span. And if you take a vector space and a subset of that vector space and take the linear span, so that will be the linear space, that will be vector subspace. If in addition that vector subspace is if in addition that ls is equals to v, then we say that the then we say that the S set actually spans V. Now another term is that linearly independent. Okay, so what is linearly independent? Now a set S is said to be, you can consider the same set, a set is said to be linearly independent, said to be linearly independent, linearly independent if for any finite set of vectors alpha 1 to alpha n, any finite set, n can be any natural number, any finite set of vectors from S, summation of ci alpha I is equals to 0 should imply that ci equals to 0 for all I equals to 1 to n. So basically what it says, one can't be written in terms of other. This is what it is mean by linearly independent. Linearly independent means that one cannot depend on other. That means one cannot be written in terms of other. Because if sum of the Ci is actually non-zero, suppose C1 is non-zero, for example, then what you can write, that C1 alpha 1 is equals to minus summation of Ci alpha I equals to 2 to n. Okay, for example, I equals to 1 to n. So now in that case, as C1 is not equals to 0, so alpha 1 can be written minus summation of I equals to 1 to n Ci by C1 alpha I. So this is a term. But because why I can write this term? Because C1 is actually not equals to 0. That means alpha 1 can be written in terms of alpha 2, alpha 3, alpha n. So that is what it is called the linearly dependence. Linearly independent means any term can't be written in terms of other terms. Okay, so this is what it is, linearly independent. And linearly dependent means that if it is not linearly independent. So basically linearly dependent, that is if S is not linearly independent, then linearly independent, then we call that is linearly dependent. For example, let's take R2. Okay, so here if we take these two set 1 comma 0 and 0 comma 1, these two element, and consider it is an S, this set is actually linearly independent, because you can't write one terms in terms of others. However, how you will try to do that, that is not possible. But if you write these two terms 1 comma 0, 0 comma 1 and 1 comma 1, this is linearly dependent. Why this is linearly dependent? Because 1 comma 1 can be written in terms of other terms. So that's why this is linearly independent, this is linearly dependent. So this is what it is, linearly dependent and linearly independent. And basis means, basis, a subset S of V is called basis if S spans the vector space V, that is linear span of S is equals to V, and S is linearly independent. So basically what it is, basis means, basis is a smallest set. I mean that can be different also, but basis is something like that, if you have a basis, that's the minimum thing you can get, and from that you will able to generate the full space, something like that. So for example in R2 this is basis, because whatever term if you want to get AB in R2, so you need to write A 1 comma 0 plus B 0 comma 1, so then you will get the term AB. So that's why this is basis. Basis is the smallest thing. This is the something like building blocks. These are the building blocks you need. This is the building. Basis is something like a set of building blocks. Building blocks can be different set of building blocks also can be possible. We'll discuss that later. But this is what it is mean by basis. So let me go back to the main problem. Main problem was that if a beta 1 is this, beta 2 is this, beta 3 is this, beta 4 is this, and this is all this, then which of the following elements belong to the row space of B? And to solve this problem, I have stated one theorem that says that if R be a non-zero row reduced echelon matrix, then the non-zero vector of R form a basis for the row space of R. So basically, row space of R, whatever the row space of R, the if we take the row reduced echelon form of that matrix, then whatever non-zero rows will be there, those things will form the basis of the row space of the matrix R. Okay, so basically, if we are getting the non-zero rows of a row reduced echelon form, that's enough, and we can take linear combination to get the row space. So I will I'll write those rows once again, but here is the, so let us consider the matrix B is equals to 1 1 minus 2 4, and this was the in the question, so I'm writing 3 2 3 4, and another is that 1 0 7 minus 4. Yeah, so this is what it is, the matrix B. So we have to do the row reduction process. As I have said, the row reduction process is that first make these two terms, first find the non-zero row of first row. So what non-zero entry of the first row? What is the non-zero entry of the first row? 1. So this is, if this was not 1, then we have to make it 1, but this is 1. So we have to now right now, what is the target? To make all other entries in that column to 0. So how to do that, all other entries to 0? Write row 2 dash, that is equals to row 2 minus 2 row 1. So this will be, let us keep row 1 as it is. So this will be 2 minus 1, that will be 0, and 1 minus 2, that is minus 1. 2 means minus 4, 9, and minus 8, and another will be 3, another will be row 3. Row 3 dash is equals to row 3 minus, row 3 is equals to row 3 minus um, uh, 3 row 1. Okay, so this will be like 0, and 3 row 1 means 3, that will be minus 1. 3 1 will be minus 6, so 3 minus 6 9. 12, 4 minus, that is minus 8, and similarly it will be subtract only. Row 4 dash is equals to row 4 minus row 1. If you subtract it 0, this will be minus 1, this will be minus 9, this will be minus 8. So this is what it is. So let's first do some quick operation. So you can look at this matrix, becomes very easy. All the 3 rows are exactly equal. So what I will do, I will write row 3 dash is equals to row 3 minus row 2, row 4 dash is equals to row 4 minus row 2. So this will be 1 minus 1 minus 2 4, 0 minus 1 9 minus 8, and all other entries will be 0 automatically. So this is the what it is. So now what you have to do, so now you have to find the first non-zero entry of the second row, that is minus 1. So we have to make it 1 first. So for example, I am making 1 right now. So this is okay, let me write in step by step, no in hurry. So minus 1 minus 2 4, 0 1 minus 9 8. So basically what I have done, r2 dash is equals to minus 1 times r2. This is what I have done. And so now what I have to do, I have to make this entry 0. So how one can do? Just we can do the addition, that row 1 dash is equals to row 1 plus row 2. So then 1 minus 1 plus 1, that is 0, minus 2 plus minus 9, if we add, then that will be okay. I think I made a mistake. This is the mistake. This is, there is no 1 minus. So then I have to do the row 1 minus row 2. Minus row 2. So this will be 1 minus 0 minus 2 minus 9, that will be 7, and 4 minus 8, 4 minus 8, that will be minus 4, 0 1 minus 9 8, 0 0 0 0 0 0 0 0. This is what it is. So so this is the row reduced form. This is in the row reduced form. Okay, so now the thing is that which of the following element belongs to the row space? So you can look at the two entries are there, 1 0 7 minus 4. This is the row space. This is in the row space. So basically what I am saying, the theorem what it says, let's take alpha 1. These are the basic element, 1 0 7 minus 4, and alpha 2, this is equals to 0 1 minus 9 8. This is equals to this. Then row space of the matrix B is actually spans by alpha 1 alpha 2. So whatever the element will be in the row space, that will be a linear combination of these vectors. So now the question, if you just look at the terms here, it is given that 3 2 5 4 1 minus 1, this is already there. We can look at 1 0 7 minus 4, this is there. So whether other terms are there or not. So for the sake of simplicity, I will write the other terms. So the options are actually, let me write options are 3, 2, 5, 4. This is one option. Another option is 1, -1, -2, 12. This is another option. Third option was 2, 1, 5, 0. And the fourth option is 1, 0, 7, -4. So this is already there. This is already there. So this is already there. Okay. So whether other terms are not, whether there are not. So you can look at whatever the alpha 1 and alpha 2 are there. So if I want to get 3, 2, 5, 4, what I have to do? I have to get the 3 into alpha 1 plus 2 into alpha 2. That's what I have to do at least. Because other, if I want to get first entry 3, second entry 2, and from these two vector, how one will get? You have to multiply 3 to the first entry, multiply 2 to the second entry. That's the basic thing. So these are the advantages one can get when you do the row reduction process. Row reduction process, something is that when you make one here and all other entry below is 0, and one here and all other entry in that column is 0, so thing is becomes like that. If you want to get 3, you have to multiply first row 3, and if you want to get 2 in the second place, you have to multiply 2 to the second row. So that I have to do. So let's do 3 alpha 1 plus 2 alpha 2. What I will get? I will get 3, 2, 3 into 7, 21, minus 18. So that is 3. And 3 into 4 minus 8 plus 16. 8 to 16 minus 8 plus 16, that will be 8. I think this is what it is. But this is not matching. So this term is not in the linear span, whether this term or not. So if I want to get for this term, what you have to do? You have to do, you have to check that, you have to at least do that alpha 1 minus alpha 2, because this is the coefficient. So what it is getting? Alpha 1 was 107 minus 4, and alpha 2 is equals to 0, 1, minus 9, 7. So what I will get? 1, minus 1, 7, minus plus 16, plus minus 4, and minus 8, 12, minus 12. But this is also not matching, because minus 2 is here, it is 16. So that's why it is also not matching. So that's why this term is also not in the spanning set. We have already seen this term is here. So whether this term is here or not, let's check. So 2 into 1, what was the term? 1, 0, 107 minus 4 plus 1. 1 means this is the first term, there is no problem. 0, 1, minus 9, 8. So what is there? That will be like 2, comma 1, comma 2 into 7, 14, minus 9 is the 5, and 2 into 4 minus 8 plus 8, 0. So this is the second term. This is exactly matching to the term. So basically these two are the correct options. Okay, other two are not. So let me write the correct options here. So till now, whatever I have discussed, is there any doubt regarding at least this is to this problem? If you have any doubt, you can ask. I will explain again. I'll at least try to explain again. Okay. And if you even have any other doubt, you can ask. I mean, other doubt regarding this course material, you can ask. I will try to explain. Okay. Even if you are not able to understand anything very easy, still you can ask. There is no shame to asking things. Okay. So let me do the another problem. I hope these are the visible. If there is any problem in my presentation, like not visible, screen is not visible, you can also ask. So I will I will I mean I will try to represent the thing so that it will be visible. So if you don't have any problem, I'm going little ahead. Even if you have the problem right now, or in some later time, you can also ask. There is no problem. I'll try to explain again. So here is the thing is that consider the matrix given in the questions 1. Questions 1 means the questions what I have done. So let me write the matrix again. The matrix was what is this question 1 means? The questions I have discussed, that is 1, 1, minus 2, 4, 2, 1, 5, 0, and 3, 2, 3, 4, and another is that 1, 0, 7, minus 4. Yeah. So these are the matrix. And what is the row reduction, row reduced matrix? Row reduced matrix R was actually 1, 0, 7, minus 4. This is the row reduced matrix. And this is the row reduced, and another term was 0, 1, minus 9, 8. 0, 1, minus 9, 8. 0, 0, 0, 0, 0, 0, 0, 0. So these are the terms. Okay. So I hope I have written correctly. 107 minus 4, 0, 1 minus 98. 0, 1 minus 98. Okay. So this is the row reduced form. So let me, so how things will become very easy right now if you have the row reduced form. This is the row reduced echelon form of A. Row reduced echelon form of A. B, sorry, not A, B. So now the question, let me read the question again. Which of the following set can be considered as a basis of row space of B? So is it clear? From here it is clear. The theorem I have said, basis of row space of B is two vector, that is one is 1, 0, 7, minus 4, another is 0, 1, minus 9, 8. So these are the two vectors. So let me match it, which it matches. So clearly it is matches with the second. And so now the question is, here is the 1074, but that is 4, not the minus 4. Okay. So this is what it is, not other, because this is exactly, because you can't get any another, I mean, you can't get another matrix from the row reduction process. You can interchange the rows, that's separate thing, but mostly you'll get this matrix only. Okay. So these are the not the options. Okay. Following set can be considered as a basis of row space of B. So this is very easy right now. Okay. And if you have any doubt, you can ask regarding this problem to the previous problem or any other problem in this course. To the even in fact any problem in the previous class I have discussed. Even if you have any problem, a doubt, you can still ask. Okay, again here is a question: the coordinate of the vectors b1, b2, b3, b4 in row space of B. Again the same matrix B here. With respect to the correct order basis obtained in question 2. What is the correct order basis? This is the correct order basis. This is the correct order basis. So the correct order basis is correct order basis is 1, 0, 7, minus 4. Another is that 0, 1, minus 9, 8. So now the question what it says, the coordinate vector in row space of B with respect to the correct order basis obtained in Qt is. So here is another new term. What is the coordinate vector? So let me write what is the coordinate vector. But if you want to get the coordinate vector, you need order basis. But what is the order basis? So let me first write what is the order basis. We have seen what is the basis, right? So let me write ordered basis. Okay. So what is the ordered basis? Ordered basis is that let V be a vector space over a field F, and beta is equals to alpha 1, alpha 2, all this way is a basis. A basis is said to be ordered basis if it is written in an order. So basically this is what it is, I want to mean, if it is written in a fixed order, and a basis and beta be a basis of V, then beta is called ordered basis if entries in beta are in a fixed order. fixed order. So then we will call the order basis. Okay. So then we'll call it is an order basis. So basically what I'm saying, for example, if you are taking R3, okay, so in that case, as I have said, the basis is actually 1 0 0. This is one basis. There is also more basis. One can also generate more basis. This is one basis. But you can write as a set. This is a set. When you are writing this is a set, one can write this way as well, right? 0 1 0 0 1 and lastly 1 comma 0 comma 0. This is also same thing. This is also as a set same. But if you are fixing an order, what is the purpose of fixing the order? That I'll tell you in couple of minutes. What is the purpose of fixing order? That I am coming a little later. But you can also fix this way, that considering this is alpha 1, this is alpha 2, this is alpha 3. Also you can consider this is alpha 1, this is alpha 2 and this is alpha 3. They are same set, but the ordering is not same. So what is the advantage or what is the importance of ordering? That I will come later. But so this is what it is mean ordering. So when you can fix the ordering, so this is what it is, the ordering. So ordering means basically this is an ordering basis. You can fix the ordering. So let me write this one on one at least can be written 0 1 0 0 sorry 0 1 0. This is the ordering. This is the ordering basis. So what is the advantage of ordering actually? Suppose you have an order basis, okay, so something like that, and if you want to write ABC, this vector in R3, if you want to write ABC, you can write like this way: 1 comma 0 comma 0 plus B 0 comma 1 comma 0 plus C 0 comma 0 comma 1. So basically what you can write ABC as an like this way: this alpha 1 like A alpha 1 plus B alpha 2 plus C alpha 3. Okay, so with this order basis we will be denoting this term as the column vector A B C. But another order basis I have said, suppose this is another order basis 0 1 0 0. Suppose this is the order basis. I'm changing again. There is no harm to change anything. This is another order basis. Okay, this is an basis. Let us give name beta dash. Okay, this is an order basis, and this is like alpha 1 dash, alpha 2 dash, alpha 3 dash. This is an ordered basis. So in that case, if you want to write ABC, how you will be writing? You have to write A 1 comma 0 comma 0. This is same 0 1 comma 0 plus C 0 comma 0 comma 1. But right now 1 0 0 is no longer the first entry of the set. This is the second entry. So A alpha 2 dash plus B alpha 1 dash plus C alpha 3 dash. So basically here I can write B alpha 1 dash. If I want to write in ordering A alpha 2 dash plus C alpha 3 dash, then it will be like BAC column vector. So this is the importance of ordering. When you are writing ordering, so you will get this type of advantage. Here terms are like 0 1 0 0. There is an ordering. I mean, if you are writing a basis, there is an advantage that you can write this way. These are called the coordinate vector. These are called the coordinate vector. The coordinate vector term is there. So these are the coordinate vector. But if you want to get coordinate vector, you have to write in a fixed ordering. So ABC is the main vector in the R3. But if you are writing with respect to this order basis, then the coordinate vector is this. If you are writing ABC with respect to this order basis, the coordinate vector is this. So let me write coordinate vector formally. Coordinate vector. So coordinate vector specifically depends on the specific order basis. Okay. So if you change the order basis, so coordinate vector will change, and there is an important relation between the change of the ordering basis. Okay. So coordinate vector is that let V be a finite dimensional vector space. Just one. Let V be a finite dimensional vector space, and let beta is equals to alpha 1 to alpha n. V be a finite dimensional vector space, and dimension of V is actually n. And let beta is equals to alpha 1 to alpha n be a ordered basis. Ordered, I have written in ordered. order basis of V, then any vector alpha in V, as I have said, as V is a vector space and this is a basis, so every element can be written in terms of linear combination of some vector, linear combination of the basis elements. So that means alpha is equals to summation of xii, I is equals to 1 to n for some x1 to xn. These are the scalar. This is called scalar or the field element. Basically, when I am writing scalar, means they are elements coming from the field. Okay. So this is the field element. And then this alpha with respect to beta, the coordinate vector is actually, this is the coordinate vector. Okay. And if I just recall to the previous fact that when I am saying R3 and 1, 0, 0, so in this case, if you are taking any vector, I mean, this is suppose R3, this is spanned by this set. Okay. Let me write it clearly. Basis of R3. And in that case, if you are taking ABC, then the coordinate vector is actually ABC. But if you are taking, this is the vector, this is the spanning, this is the basis set, this is the order or basis like 0, 1, 0 and 1, 0, 0 and next is like 0, 0, 1. If you are writing like this way, in that case, if you remember the ABC, if you are taking, in that case the coordinate vector is actually BAC. Okay, this is what becomes the coordinate vector. So that's why this is something very not natural, but this is something very natural. So that's why these type of bases are called standard ordered bases. Okay, that 1, 0, 0, 0, 1, 0, 0, 0, 1. This is called standard ordered basis. This is also ordered basis, but this is ordered basis, not standard. Standard means in that standard terms comes from this finite dimensional vector space like R to the power n, F to the power n, C to the power n. From there, standard order basis things are coming from. Okay, so this is what it is I mean by coordinate vector. So this is specifically depends on the order basis. So if we change the order basis, coordinate vector will change, and there is a relation that will come when those type of problem will appear. So now let's go back to the main problem. So what was the questions here? The coordinate of vector beta 1, beta 2, b1, b2, b3, b4 in row space of B. So B was the matrix. This was the B matrix. This is the row space. Okay, and so row space, basis of the row space is actually this. This is, if I write in order basis, this is the alpha 1, 107 minus 4, and beta and alpha 2 is actually 0, 1, minus 9, 8. This is the alpha 2. Now, if one wants to get B1, B2, B3, B4 from these two terms, what you can say? That you at least need B1 alpha 1 plus B2 alpha 2. So in that case, what it will be? B1, B2, 7 B1 minus 9 B2, minus 4 B1 plus 8 B2. I hope I'm correct. Yeah, I'm correct. So whatever this term, that doesn't matter. If you want to get B1 in the first place and B2 in the second place, you have to write like this way. You have to get the linear combination this way. Okay, so this is what is the main point. So coordinate vector with respect to these two bases, what will be the coordinate vector? So this has to be B3 and this has to be B4. If this is not matching with B3 and B4, the third term and fourth term respectively, in that case, this vector will not be in the spanning set. But here it is given that this vector is in the row space. This is given. Okay, this vector is in the row space. If this third term is not matching with B3 and the fourth term is not matching with the B4, in that case, it's clear that the vector B1, B2, B3, B4 is not in the row space spanned by alpha 1, alpha 2. Okay. So in that case, so at least you need B1, B2. So the coordinate vector, if you are writing, suppose this is B3 and B4 matching, I'm taking. So in that case, what you need, you have to multiply B1 with alpha 1 and B2 with alpha 2. So that's why the coordinate vector with respect to this order basis is that actually B1, B2. So where it is written in row vector wise. This is what it is. Third option is again correct option. Okay. Is it clear? Because here it will be little complicated, because if you see that if you take b1 alpha 1 plus b2 alpha 2, in that case you will not no longer get b3 b4. But it's clear that if you want to get this type of vector from the row space of the matrix B, which is actually this was the matrix, whoever comes later, for those I'm saying, this is the B matrix, 1 1 minus 2 4 and 2 1 5 0 3 2 3 4 and 1 0 7 minus 4. Okay. Okay. Okay, so and the row reduced form is this, so that's why the row space actually spans by these two vector only. So now the thing is that b1 alpha 1 plus b2 alpha 2, if you want to get this type of vector, you have to multiply b1 with alpha 1 and multiply b2 with alpha 2. So that's why this is here. And this third and fourth term, whatever it will come, that has to be equals to b3 and b4. If it is not equals to b3, for example, you are giving like some vector, like already we have discussed, that b3 and b4, if you are given like b1 and b2, and here is some term, here is some term, b1 is some, suppose 2 and b3 is 3, so in that case these two terms are not matching with these two terms. In that case we can say that this term is no longer in the spanning set of the row space of B. I hope it is clear. So no other option is possible. That's clear very much. So even it is not clear, even the question sounds very simple from your side, you can ask. If it is not clear to you, you can ask. Okay. Or even the screen is not visible, you can say, then I'll try to represent again. Which one? This one. Okay, so let me recall a little bit. This was the matrix B given. Okay, so this is the first row. I hope it's visible, right? First row is 1 1 minus 2 4. Second row is 2 1 5 0, and third row is 3 2 3 4, and fourth row is 1 0 7 minus 4. So the question is that initial question was that what are the row space? Some questions was like that. So if you want to get the row space, what we have to do? We have to do the row reduction process. And after row reduced echelon form, this is the row reduced echelon form. We have done the row reduction process little earlier. So this R matrix is actually the row reduced echelon form. So in the row reduced echelon form, whatever the non-zero rows will be there, they are the only, I mean, they are something basis of the row space. This is a theorem. If you have a matrix, you are doing the row reduction process, and the and at the end of row reduced echelon form, whatever the non-zero rows will be there, they are the basis of the row space of the matrix B. Row space. What is row space? Row space is actually the space which is spanned by the rows of the matrix B. So now in this case, this matrix B and the rows are this. The row space is actually spanned by this vector only, because these are the two non-zero vector in the row reduced echelon form. Now if one wants to get some vector, suppose 2 3 5 4, suppose this is a vector. Question is whether this vector is in the row space or not. So if it is in row space, that has to be linear combination of, at least that can be written as a linear combination of these two vector, like 1 0 7 minus 4 and 0 1 minus 9 8. Okay, this is the thing. So now if 2 3 5 4 2 3 5 4 is actually linear combination of these two vector, then what I have to get? I have to at least take 2. I have to write like this way, and 3 0 1 minus 9 8, because this is the only way one can get 2 at the first place and 3 at the second place. You have to multiply 2 here, you have to multiply 3 here, otherwise you will not get. That's the importance of the linear independence and dependence actually helps. So but if you do that, so what will be the third term? Third term will be 14 minus 9 3 18, so that will be minus 4. So this is not matching. Fourth term will also be not matching here. Minus 8 plus 24, so that will be 16. So fourth term will be 16, so that is also not matching. So if this term will be inside like minus 4 comma 16, 2 comma 3 comma minus 4 comma 16, this term is in the row space, but 2 comma 3 comma 5 comma 4, this term is not in the row space. Okay, now the question is, this is one part which I have discussed little earlier, this type of questions, that 2 comma 3 comma 5 comma 4 is not there. This is the first clear, but 2 comma 3 comma minus 4 comma 16, that term is there, because that can be written like this way. Okay, now the another question is that suppose you are giving like this, suppose you are giving like this is a vector, and 2 comma 3 is given, and here is some term b3 comma b4 given, and you are already told that 2 comma 3 is in the row space of the matrix b, this is already told you. Okay, you don't need to doubt about those, that this term is in the row space of the w, row space of the base of b. Now the question is, what is the coordinate vector? And if you remember, what was the coordinate vector terminology I am explaining? That if you have a order basis like alpha 1 and alpha 2, alpha 1, alpha 2, alpha n, then an alpha is a vector. If you are writing alpha, then it's clear that as this beta is ordered basis, then any element in V can be written in terms of some scalar multiple of orthonormal scalar multiple of ordered basis. So these are the scalars. Scalars means the elements from the field over which the V is a vector space. Okay. So xi are that scalar, whatever I am saying. Then writing x1, x2, xn in this way called the coordinate vector. Okay. So now if you are getting, you are asking that 2 3 comma 2 comma 3 comma b3 comma b4, this is already, you are already told that this is already in the row space, and these are the vector in the these are the ordered basis in the space of the row space of the matrix B. So then what will be the coordinate vector of this vector if you want to write is as a linear combination of these two vector 1 comma 0 comma 7 comma minus 4, 0 comma 1 comma minus 9 comma 8. So then it's very much clear that that has to be 2 comma 3, because you have to, if you want to get something like that, if you want to match first two terms, then you have to multiply 2 to the first term and 3 to the second term. So this is the coordinate vector. So is it clear? Or if you have any specific type problem, you can ask. I'll try to explain. I don't. So, I mean, basically, thing is that there B3 and B4 does not depending. I mean, does not um, defining the coordinate vector. Coordinate vector is actually in this particular situation actually defining by the first two vector, first two entry. This is what is the main issue. Okay, is it clear? Otherwise, I'll explain. Not a problem. Okay. Yeah. So let me go to the next problem. If you have any problem till now, you can ask, or if you have any problem till regarding the in this course or anything you have not understand from the main course lectures, you can still ask those things. I'll try to try to explain. Okay. Again with the same problem. I mean same matrix. Here is the main matrix one is there. So let me write once again the matrix, whatever the matrix, because that was the under the same main questions we are discussing all the sub questions basically. The B was the matrix. B was the matrix was the like 1 1 minus 2 4, and B2 is actually 2 1 5 minus 2 4 2 1 5 0, and next term is actually 3 2 3 4. This is the B matrix 1 0 7 4. This was the matrix 7 minus 4. Yeah. So in after row reduction, what we got 1 0 7 minus 4 0 1 minus 9 8, or just let me check, minus 9 8. Okay, minus 9 8, and next is next all other term. This is the row reduced form that we have done in the um, starting at the starting of the course. This is after row reduction basically, row reduction. So now let me start the read the questions once again. So what is the question says? Consider the matrix B. This is the matrix B. Which of the following sets can be considered as a basis for the solution space of Bx equals to 0? So we have a new question, new type of questions basically. So now here x means basically, here x means actually x1, x2, x3, x4. This is column vector. So now here is the question is that what is the basis of the solution space? So let me write why one is saying that basis. Whenever you have Bx is equals to 0, so solution space, this will be subspace. Why this will be subspace of R4 or whatever the vector space? Solution space R4 basically, solution space, because if x1 is a solution and x2 is a solution, solution means that is bx1 is equals to 0 and bx2 is equals to 0. That means the solution space. So solution space is actually all those vector x in R4 such that bx is equals to 0. This is solution space, and this will form a vector space. This is what I'm saying. If you have x1 equals to bx1 equals to 0, bx2 equals to 0, and c is a scalar, means element from the field, that is here R basically, or even c is also okay, not a problem. So now you can look at that b plus cx1 plus cx2. B is an n by n matrix. X1 is a column vector, x2 is a column vector, and c just a number. Okay, that can be real or complex. That doesn't matter. That depends on the space. But here I'm not interested, not much there. So this will be bx1 plus bx2. As x1 and x2 are solutions, so this will be 0. So that's why this will form a subspace of R4. Okay. So subspace, that is not our questions basically. Main question is what is the basis of that subspace. So what is the solution space? Once again, solution space is equals to all those, here it is written, yeah, let me write, x is in R4 such that b of x is equals to 0. This forms a vector subspace of R4. Vector subspace of R4. This is what I have discussed in this right hand side, that if you have two vector, what if you recall the previous class, what we have said, that if you have a subset is said to be subspace of a vector space if you are taking two vector alpha, beta, and a scalar. Scalar means element from the field C, such that C alpha plus beta is once again in the main set. I mean, W is subset of V, then W is said to be subspace if for any alpha beta in W and C in the field, we should have alpha, C alpha plus beta should be in again W. So this is what I am proving here. So that's why that's why the solution set becomes a subspace. So whenever you have a subspace, you have a basis possibly. Okay, because R4 has a basis, so therefore here also will have a basis. So we have to find the basis. So that means, once again, what is the basis? Basis means a set which is linearly independent that will span the main set. Okay. So this is the row reduced form. As I have said, the row space after row reduction, okay, so once again, recall one more theorem. Let let be a row reduced row reduced echelon form of a matrix A, then the solution space basically x belongs to R4. Here it is whatever it is main. So as I am saying theorem, so matrix A of order m by n. So here xn will be xrn such that, or what is the field basically, field n such that rx is equals to 0. That means the row reduced form. This is exactly equals to x belongs to fn such that ax is equals to 0. So basically solution space for this set is same with the solution space of the row reduced echelon form. So therefore in that case solution space x belongs to R4. So in our case, let me write it clearly. In our case, Ax belongs to R4 such that Bx is equals to 0. This is exactly equals to x belongs to R4 such that Rx is equals to 0. And recall what is the Rx? 107 minus 4, 01 minus 98 and 000 something like that. So let me write R once again. R was 107 minus 4, 01 minus 98, 0000, 0000. This was the R. So let me write one x1, x2, x3, x4. This is equals to 0000. This is what it is. So what I will get? I will get x1 plus 7x3 minus 4x4. This is equals to 0. Another equation is x2 minus 9x3 plus 8x4. This is equals to 0. So this equation will give x1 is equals to 8x4 minus 7x3, and this equation will give x2 is equals to 9x3 minus 8x4. So one thing you can look at from here, that if you want to get solution space, means you have to find some vector x1, x2, x3, x4 which should satisfy this relation, and which turns out to be which should satisfy the Rx is equals to 0. This is what it is turns out to be, right? So now the thing is that, so we have to find x1, x2, x3, x4. This was our main target. But if you look at the calculation, what leads to us that x1 depends on x3, x4, and x2 depends on x3, x4. So if you fix the value of x3 and x4, then you will automatically get x1, x2. Okay, and if you are, I mean, x1, x2 is depends on x3, x4. So what is the independent variable here? What can be independently that does not depends on anyone else? That, I mean, in that way, x3, x4 can be said that independent. You can also convert x3, x4 to the in terms of x1, x2. In that case, x1, x2 will be dependent, but forget about those things. So what it says that basically this is a solution. So solution space is 8x4 minus 7x3, 9x3 minus 8x4. This is x1, x2, another is x3, x4. So this is the solution space. This is a vector space. So sorry. Thank you. Yeah, otherwise I'll get the wrong answer. Yeah, thank you so much. 4x4 minus 7x3, 9x3 minus 8x4. I think you are correcting this one, right? I hope this is what it is correcting. So solution space is something like that, and x3 and x4 are actually free to move. They can be any number from R3. So that you can, if you have heard something like that, if you have whatever the number of free variable, that's the dimension of the space. But you can write very sophisticated way. That you can write this term in this way. Write x3 into minus 7, 9, 1, 0 plus x4, 8 minus 4, 0, 1. You will get these two terms. Okay. So these are something like called, so whatever the term you can choose. So these are some basic term. So whatever these are solution space contains this type of vector, right? So if you choose any vector, that can be written in terms of, this is general terminology. Now you can choose x3 and x4 as your wish. You can choose 1, 0, 1, 1. You can choose both of them are 1. You can choose both of them are 0. 0 is always solution. There is no doubt about this. And you can choose 1, 0, 0, 1, 1, 1, 2, 3, whatever you wish. You can choose x3, x4. But these are the basic thing. So that's why, yeah. Sorry. 4, and this was the 8, right? I have changed incorrectly. Yeah, thank you. 4x4 minus 7x3, 9x3 minus 8x4, 4x4 minus 7x3, 9x3 minus 8x4, x3, x4. So this will be minus 7 x3 I'm taking, my 9, 1, 0. This will be 4 minus 8, 0, 1. Yeah, I hope I am correct right now. Let me check the answers if it is answer correct. Minus 7, 9, 1, 0. Yeah, here it is matching. 4 minus 8, 0, 1. 4 minus 8, 0, 1. Yeah, this is so therefore the basis of the solution space is, you can take minus 7, 9, 1, comma 0 and 4 minus 8, 0, comma 1. This is the basis. So why I am saying this basis? This is linearly independent, that you can check. I will not check because here is the term 1, 0, 0, 1. This will make the linearly independent. Why I am saying this? If you multiply C1, C2 and make it like, if you write this one as the alpha 1, this one as the alpha 2, I mean, they will be linearly independent. There is no doubt about this. But I'm just for formality, I'm saying, if you want to check, Then if you write cu alpha 1 plus c alpha 2, last two term will be like, there will be some term, and last two term will be like c1 comma c2, and this has to be equals to 0 comma 0 comma 0, something like that. So then c1 has to be 0 and c2 has to be 0. So that will make sure that alpha 1 alpha 2 are actually linearly independent. And also there is more other way you can check, but yeah, they are linearly independent and they spans the set. They spans the set because, as I have said, any element which is in the solution space, they has to be like this way. They has to be like this way, and that can be obtained by taking linear combination of these two vectors. So this is what it is. So the correct option is final one. Other option is possible, but this is not correct. You can check. Other option will not be correct because you can check like you can easily replace those terms here, and you can check other terms. They will not satisfy. For example, let me write the one of the options for the first option. What was the first option? First option was that, I mean, fourth option is the final option. That's correct. But why the other option is not correct? So that you can check by replacing those value here. So what was the that minus 7 9 1 comma 0? This is the first vector. Option A was like this, and the second vector is that 3 comma 1 comma minus 1 comma minus 1. This is the option B, second option. First is correct, but second is not correct. Why second is not correct? Because if you replace this 3 1 minus 1 here, just replace, uh, so what you'll get, x3 will be minus 1, x4 will be minus 1. Okay, so then 4x4 minus 7x3, what it is becoming? Minus 4 plus 7, that will be 3. That's matching, that's good. 9x3, sorry, okay, 9x3 minus 8x4, 9x3 is equals to minus 9 plus 8. This is becoming minus 1. So, but here it is plus 1. So that's why it is not matching. Okay. So similarly, you can check other option also. Like B option was like 3 minus 1 minus 1 1. So here it will also not match, because if you take x3 is equals to minus 1, x4 is equals to 1. So this is what it is suggesting to take this. I'm not taking by myself. This is what it is suggesting to take. And then what you'll get, x1 is equals to, this is what it is x1, and this is what it equals x2. That is not matching. So x1 is equals to what you'll get, 4x4 minus 7x3, right? So 4x4 is 1, 4, 7x3 plus 7, that is equals to 10. That not matching with 3. That's why this is second option is also not correct. Similarly, third option is also not correct. Okay. So any doubt till now you have, at least regarding this last problem what I have discussed? Yeah. If you have any problem regarding this problem, to the previous problem, or anything to the content of the main uploaded lectures, if you're not able to understand anything from that's there, or if you're not able to understand any problem solved there, you can ask here. I will explain here. Even the very simple questions you can ask, because it's better to ask, and I mean, it's better to ask if you, instead of staying in the doubt for the whole, say, whole course or semester basically. Okay, so let me go to the next problem. Till now, if you have any problem, you can ask. Yeah. So this is the another questions. Now we have completely new questions. What it is says, let V be a vector space of all 3 by 3 matrices. 1 second. Yeah. So let V be a vector space of all 3 by 3 matrices over the field F. W1 is actually this. This is subspace. And W2 is this. This is a subspace. Now the questions, these are the two subspace of B. Now the question is then, which of the following statement is or are incorrect? Let me know the incorrect, not the correct. Which is not correct? So as I have said, in general, the free variables are the number of free variables are the basis, because this is the subspace. Why? So I am not checking. This is also mentioned that they are subspace. This W1 and W2 are subspace. So I am not checking those things obviously. So what are the basis of this W1? W1 basis will be, you can write W1, any element in W1, you can write any element in W1 like this way: 1, 0, 0, 0, 1, 0, 0, 0, 1 plus x2 0, 0, 1, 0, 0, 0, 0, 0, 0 plus x3 0, 0, 0, 1, 0, 0, 0, 0, 0 plus x4 0, 0, 0, 0, 0, 1, 0, 0, 0. You can write any element in W is actually this way. W1 is actually this, such that x1, x2, x3, x4 are real. This is what it is. W1 you can write. This is one can write is the W1. Now the question is, it's clear that if you write this is as alpha 1, this is as alpha 2, this is, let me write it in color. This, if it is in alpha 1, this is alpha 2, this is alpha 3, and this is alpha 4, then it's clear that alpha 1, alpha 2, alpha 3, alpha 4 spans the set W1. Similarly, one can write same situation for the W2. But the question is, does they are linearly independent or not? This is sub. So if this is linearly independent, if these vectors are linearly independent, alpha 2, alpha 3, alpha 4, if these vectors are linearly independent, then they will be basis, this set will be basis. And if this set is basis, okay, what is the dimension? Dimension, so here is one important theorem. I have said that you have a vector space V which is finite dimensional. That means there exists a basis which has some finite number of entries and they are linearly independent and they spans the set. This is what it is. One important fact is that if you have a vector space, I have said that there may be possibly 2-3 type of vector bases. But when you are considering finite dimensional vector space, then whatever the basis you can consider, every basis will have a fixed number of entries, fixed number of element. So that is what it is called the dimension. For example, if you are considering R3, in that case 1, 0, 0, 0, 1, 0, and 0, 0, 1, this is a basis because this will form any element. If you are taking in R3, you can write linear combination of these vectors. You can also take, this is a basis basically, basis. You can also take 1, 1, 0, 1, 0, 1, and 1, 0, 1, 1. This is again a basis. You can take 1, 0, 0, 1, 1, 0, and 1, 1, 1. This is again a basis. So in this way you can construct many bases. But whatever the basis you will construct, the dimension, the number of entries in that basis will be fixed always. That is itself a fixed theorem, and that one can very easily prove. There is not much hard, but I will not prove that. So main thing is that, main thing what I am saying, if you are taking finite dimensional vector space, you will get a say finite set uh, which which entries are linearly independent, and that those entries spans the vector space V, and that set is called a basis. The number of entries in that basis is called the dimension, because the number of entries any basis of a finite dimensional vector space will be fixed. That is why it's called the dimension. So that's why if you are talking about dimension of R3, that's clearly 3. So if I can prove that alpha 1, alpha 2, alpha 3, alpha 4, they are linearly independent, they linearly clearly spans W1. If they are linearly independent, then they will be basis. This is what it is, my target. So whether they are linearly independent or not, how one will check? So you can take, instead of x1, you can take c1, c2, c3, but it is vector space, that doesn't matter. If this sum is equals to 0, we have to show that all the xi equals to 0 for all I equals to 1, 2, 3, 4. And that will be, you just look at, this sum is actually this. If you write this is as a 0 matrix, then what will get? x1 will be 0, x2 will be 0, x3 will be 0, x4 will be 0. That's very much clear. If this is equals to something like 0, 0, 0, 0, 0, 0, 0, 0, 0, then you will automatically get x1 equals to, because when two matrices are equal, that means they are point wise, component wise equal. So that means x1 equals to 0, x2 equals to 0, x3 equals to 0, and x4 equals to 0. So that means you have the dimension of W1 is actually 4. So that means this is a correct option. So that is not our option, because here a question is asked to find an incorrect option. So this is not our option. Okay, 1 second. So this is not our option. So correct option is actually, okay. Similarly, if you take W2, you will similarly check that dimension will be W4. So that's why this is also not a correct option. This is also not a correct option. Now let me go to the set W1 plus W2. So now we have W1 plus W2. W1 plus W2 means the sum of two entries, basically. So what is W1 plus W2? W1 plus W2 is actually W1 plus W2, that is actually just W1 plus W2, such that W1 is coming from W, capital big W1, W2 is coming from big W2. This is what it is, W1 plus W2. So now if you take like this way, so if I take W1 plus W2, what it will be? W1 plus W2, in our case it will be, I'm writing like x1 plus y1, y2, x3, x3, x1 plus y1, x4 plus y3, yeah, x4 plus y3, and y4, 0, x1 plus y1. Okay, this is what it is. x1 y1 can be any entry, x1 y1, x2 y2, x3 y4, everything is real number. But what is the dimension of this space? This is what it is, the important question. Interestingly, dimension of this space is actually again 4. Why? Because they are same term, they will be considered contribute to 1. So one can write this set x2, x3, x4, y1, y2, y3, y4, all are coming from real number. This set is actually exactly equals to something I will write new, a1, a2, a3, a3, a1, a4, a, one second, no, 5 it will be, sorry, 5. So yeah, 5 it will be, sorry, this is not 4, this is 5. A5, this is 0 and this is A1. One can write always this way. There is no harm to writing this way. And A1, A2, A3, A4, A5, they are real number. If you have any doubt why you can write this way, I will try to explain. The thing is that, let me quickly say something, so at least one can say that. So x1, y1 you can choose freely. That doesn't matter. But you have to whatever the matrix term, that has to be, that this diagonal term has to be same. So that's why I have replaced them by a1, a1, a1. And so look at carefully that no terms are actually involved to other. I mean, they are x3 and x3 they are appearing. Y2 appears only here. No other place y2 appears, right? Y4 appears only here. No other place y4 appears. X4 and y3 appears here. No other place they will see. In fact, separately they did not appear any place. Okay. So that's why they will not create any problem to considering this way. So that's why, so that in clearly dimension of W1 plus W2 is actually equals to 5. Okay. Now, there is one important theorem. I can discuss that also. I can do directly also. Let me do directly. So this is the correct option. Oh, sorry. Mm, one second. Just a minute. W1 plus W2, which are incorrect. One incorrect will give the other incorrect. Okay, let me write x1 plus y1. Let me write once again. x1 x1 plus y1. This is the first term. Y2, x2, x3, x1 plus y1, x3, sorry, y3 plus x4, y4, 0, x1 plus y1. This is what it is. So main diagonal give 1 entries, y2 give will y2 x2. That is the mistake I made. Sorry, I made a mistake. This is what it is, not x3. This is what it is, x2, I think. Yeah, this is what it is, x2. That is one. Then x1 plus y1, y2, x2, x1 plus y1, y2, x2, y2, x2. Yeah, that will be that is what I'm saying, the other way one can do, but just directly what I'm saying. So then you can use the that will be easy, that definitely, but that you have to use the theorem that dimension of W1 plus dimension of W2 is equals to dimension of W1 intersection dimension of W2, dimension plus W2. That hmm, hmm, no, that's what not happening. That's what I'm saying. Here, here I'm saying, let me write here alpha 2. Sorry, this is alpha 3. This is 4. So I'll change everything. So I'll change because this is one mistake I made. So alpha 3, alpha 4, alpha 1, alpha 5, alpha 6, alpha 7. Yeah, this is what it is we have, right? No. 1, 2, 3, 4, 5, 6, 7. Oh, sorry, this is 1. So this is what it is we have, right? This is what it is we have. So why there will not be problem? Because you are free to choose x1, y1. Okay. So now, even, I mean, they are not involving here. If you look at carefully, x1, y1 only appears here only as a sum. Okay. Y2 appears only here. No other place is there where Y2 appears. There is no other place. X2 appears here only. No other place X2 appears. X3 appears here only. No other place X3 appears. Y4 appears here only. No other place Y4 appears. And similarly, X4 and Y3 there appears there, but no other place. There appears simultaneously. So this way. But if terms are involving, here terms are luckily not involved. So if terms are involving, in that case, this technique will not be good for actually to do that. So basically here the dimension is actually 7, sorry 6. So that's why the first question is not correct. But as you have said, so we have to find anyway that dimension of W1 plus W2 intersection W2. So let me write what is the W1 intersection W2. That is, uh, that means that x1. Let me write the quickly the terms here: x1, x3, x2, x3, x1, x4, 0, 0, x1. This is one term. Another term was y1, y2, 0, 0, y1, y3, y4, 0, y1. Yeah, these are the term. So now clearly these are the W1, W2. So first place will be non-zero. So that's why I'm writing that is some new term like A1. This is another way I'm writing A1. Second place, you have to take intersection. That says that we have to take the 0 in the second place. Third place, we have to take intersection. That's why you have to take 0. Fourth place, we have to take intersection. So that's why it will be 0. Fourth place will be same. So that is A1. Fifth place, x4 and y3. So they are free. So that means there will be another new term A2. And fifth, fourth, this sixth and seventh place will be 0 and here will be A1. So this is what it is, dimension. So here A1 and A2 are coming. They are free. This is what it is, W1 intersection W2. So they are free here. It is A1, A2 free. That says that dimension of W1 intersection W2 that's equals to 2. So that means answer is that this has to be 6. If the answer has to be, I mean, if the answer was asking correct, that has to be 6 and that has to be 2. But this is not the case. So that means these are the incorrect options. So here it is asked which are the incorrect options. So this is not correct. Other way, just if you know that W1 intersection W2, or if you know that dimension of W1 plus W2, there is an important theorem, very important theorem. You have to find at least one, W1 intersection W2 or W1 plus W2. But it's true that W1 intersection W2 is very easy to find in compared to W1 plus W2. So theorem says that if W1, W2 are finite dimensional subspace, W1 and W2 are finite dimensional subspace of V, then dimension of W1 plus dimension of W2, which we have obtained in our case, this is 4, each of them are, is equals to dimension of W1 plus dimension of W2 plus, sorry, dimension of W1 plus W2 plus dimension of W1 intersection W2. So for example, if you know this is 2 and you know these two are 4, so in that case this has to be 6, and if you know this is 6 and this is 4, you will get this is 2. So that means finding option, finding checking checking this one W1 plus W2 or checking W1 intersection W2 is enough. At least one, I mean, you can check one and solve the problem. This is what it is. I think you are suggesting, I think Arun, yeah, you are suggesting to this process, right? Finding W1 intersection W2 and then using this theorem. Am I correct? Okay. Yeah. Thank you. So if you have any problem in this, if you are not able to understand anything from this problem or any previous problem, you can ask. Okay. If you have any problem, you can ask. Otherwise, I'll go ahead to the next problem. If you have any specific problem from the class, any specific problem from the linear algebra, yeah, anyone raising hand or it's okay just for by mistake? If anyone raising hand, then okay. Otherwise, I believe this is by mistake. Okay. So this is another problem. What it says, let W be a subspace of a vector space C3, and so for my convenience, I will write this is W1 and this is W2 because writing is okay, but these two symbol is not possible to spell out. At least box one, you can say box one, box two, whatever it is, doesn't matter. Okay. The question is, you have these two set W1 basis of a basis, two bases. Basically, you have two bases. So here is the interesting part comes that once I said that you have a vector space or subspace. Specifically, for example, for right now, you can consider that as finite dimensional, and you have two bases. As I have said, you have if you have two different order bases, you will have a coordinate vector corresponding to each of them. But what is the relation between them? Okay, let me first write those things, and later I will come to this problem once again. So let W be a vector space or subspace. You can take vector space with dimension of W is actually n. Let beta is equals to alpha 1 all the way alpha n. This is not vector, this is scalar, and beta prime is equals to alpha 1 prime all the way alpha n prime are two ordered bases. Okay. Any terminology, if you are feeling that any terminology does not, you don't know, you can ask here, not a problem. Ordered basis. Then for any vector, for any alpha belongs to the space W, alpha can be written as some scalar linear combination of these vectors I equals to 1 to n. Also, as this is an order basis, alpha can be written this way as well. Xi dashed, alpha I dashed, I equals to 1 to n. So here both xi and xi dashed for I equals to 1 to n all are coming from the set R. Now, alpha with respect to the first vector called the coordinate vector. This is the coordinate vector called the coordinate vector. This is called, and here alpha with respect to this basis, the coordinate vector is this is the coordinate vector. Now, the question is alpha vector is fixed. I mean, W is a main vector space, alpha is an element there. Someone came with an order basis and another person came with another order basis, and you have some two different type of representing coordinate vector. These are representing coordinate vector. So, but what is the relation that one can ask? So, the relation is that there exists an invertible matrix P. So, there exists an invertible matrix. Let me write this is as X and this is as X prime. Matrix P called basis change matrix from beta to beta dash basis change matrix from beta to beta prime, beta to beta prime. That is sometimes denoted by basis change matrix. What is beta beta prime denoted by called basis change matrix from beta to beta prime, such that ax is equals to px dash. So this is what it is, but how this is coming, I'll quickly say. Okay, if you have any doubts still you can ask, because these are very important thing. And as I have started with that, alpha is a fixed vector. You are writing in terms of the one order basis. This is what it is, the coordinate vector coming. With respect to another order basis, another coordinate vector is coming. So what is the matrix P actually? This is a theorem, but what is the matrix P? So as I have said, starting with the beta is a beta alpha 1, alpha 2, alpha n is an order basis. Alpha 1 dash, alpha 2 dash, alpha n dash, another order basis. So for any j in equals to 1 to n, alpha j dash, they must be can be written in terms of alpha with respect to some linear combination, because alpha j is also the elements in the vector space. Okay, and alpha is a basis. Alpha j dash may be basis, that doesn't matter. They are element, so they can be able to write in terms of alpha I as a linear combination of. So that is what it is. Let me write it as pij I equals to 1 to n. Okay, this is the pij entry. So now if you write this way, then an alpha is equals to summation of xi dash alpha I dash alpha j dash, let me write it, j dash j equals to 1 to n. This can be written as summation of xj dash into summation of I equals to 1 to n pij alpha I and j equals to 1 to n. This can be written as summation of I equals to 1 to n pij xj dash whole into alpha I. But remember, alpha has the another. So we have started with the linear combination in terms of second basis. We came with the first basis. Already we have this fact that xi alpha I j equals to, or j equals to, or I equals to, you can write I equals to 1 to n, I equals to 1 to n xi alpha I. This was the thing. So you can compare. Alpha is the linear independent vector, so you can compare that xi, that implies that xi is equals to, oh sorry, here I have made a mistake, summation of j equals to 1 to n. Yeah, you can know that j equals to 1 to n pij xj dash. So this is true for all I equals to 1 to n. So this is what it is. If you write as a column vector x1, x2, xn, then you will get that this is the matrix P with the vector x1 dash all the way xn dash, and P is the matrix with I jth entry is actually Pij, this Pij. So this is the basis change matrix. Okay, but I don't. Maybe the question is not asking something like that. But as I have said, that I will discuss the theorems in between questions according to the need. Okay, here it is maybe not that much is asking. Okay, but here just basis change matrix. This is something natural. One can come. So that's what I'm saying. So you have these two bases. Okay, and you are asked with respect to this first basis how to write this one. You have the question 5 2 minus 3i comma minus 3 plus 3i. Okay, this one you have to write in terms of first basis. So it is clear that as the second place is 0 in the first vector of the first basis, and the second vector of the second basis is 1, so that's much clear that if you want to get second vector 2 minus 3i, you have to write that 2 minus 3i times the second vector. What is the second vector? 1 plus I comma 1 comma minus 1. And what is the first vector will be? So let me write what is the first vector is needed. First vector, sorry, yeah, you want to express this term in terms of the first vector, right? So if you, so from here you can look at the thing is that how one will get the first vector quickly. It is possible, generally it is possible, there is no harm. So okay, let me write. So it's clear that second term is 2 minus 3i. So let me, one can check with this because this is suggesting. you can start with the vector that this is some x1, and you can start with 1 comma 0 comma I, and you can calculate. Let me calculate this term. Basically next one I will not calculate. So this one will be like this one will be like x1 plus 2 plus 2 plus I, 2 plus 2I minus 3I minus 3I square. This is the first term. Second term is 2 minus 3I. Third term is I into x1 minus 2 plus 3I. This was the thing. And we have to get this is equals to this. So then what I will get, 2 plus 3I is clear. Then what I will get, x1 is equals to 5 minus 2 minus 2I plus 3I minus 3I square plus it will be. So this will be like 5 minus 2 plus I, and I square is equals to minus 1. So this will be minus 3. So this is cancel out. This is I. Okay, so basically x1 will be I. So this is the correct option. So as the coordinate vector of a fixed order basis, always fixed. So even if you do the second times with respect to that order basis, this is not the correct option. This is no need to check second option. Okay, so this is the correct option. Second option is not the correct. Okay. Now for the second option. So for the second vector, this is one vector we have to check because this is what it is. You can look at. Other thing is that other we have two other vector. Here actually complex. Here it is written over C vector space over C3. So over real it will not form. You can start V is a set is equals to C3. This will not form a vector space over real because no, this will form a vector space over real. That will definitely form a vector space over real. Sorry, I made a mistake. This will form a vector space over real, but here it is as yeah, that's true. Your question is genuine because here x1 is taking I. So if the vector space is real, then this is not in the linear span. Okay, at least this vector will not be linear span. So in the complex case, yeah, so this will form C3 will form a vector space over real, that's true. There is no doubt. But here it is considering over C3. It's complex. C3 will form a vector space over real. There is no doubt about that. Yeah, they're constant from coming from C. So other two vector is there. They are asking for the second root. So here is no place. So let me write it in the. So uh, other two vector was 1 comma 0 comma I. We have to do it with respect to the another second order basis, that is box written in the questions. That was 1 comma 1 comma 0. Another is that. Another is that 1 comma I comma 1 plus I. Let me check whether yeah, this is correctly. So another this is another vector we have to check with the second basis, and another vector we have to check 1 plus I comma 1 comma minus 1. This is another vector we have to check. These two vector, these are the two third option. This is third option and this is the fourth option. With respect to if we try to find with respect to this order basis, if we try to expand this, what will be the answer? So that's the question. So let me clearly tell you the second option is not possible. Second option C 10I. I want to get 10I in terms of 110 1I 1 plus I. 1 second. Oh, 10I. Sorry. Okay. So if you want to get second, so let me write formally. A 1 comma 1 comma 0 plus B 1 comma I comma 1 plus I. So that gives that A plus B comma A plus I comma 1 plus I. So this is what is the problem. I think there is a mistake. Just a minute. Question, there is a mistake in the question. So it's not mistake. One cannot say the mistake. But option A is correct. So automatically option B will be discarded. There is no doubt. But the option C is not correct. 1 comma 1 comma 0 1 I 1 plus I. Yeah. So okay, if you want to get this one, so what you have to get, a plus b has to be 1. This is first place. A plus I has to be 0. So that says a is equals to minus I, right? And 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 third option says 1 plus, sorry, third option says b into 1 plus b into 1 plus I is actually I. So what will b is equals, if a is equals to minus, oh, this is correct. Yeah, I am maybe mistake. If b is equals to 1, a plus b is equals to 1, a plus bi, yeah, this is the simple mistake I'm making. So that's why I became too much confusion. So this is equals to a plus b, second option a plus bi, third option b into 1 plus I. Okay, this has to be equals to 1 comma 0 comma 1. So that says a plus b is equals to 0. Another says that a plus bi is equals to, sorry, that says a plus b is equals to 1. Another says that b into 1 plus I is equals to I. So how one will get b from here? B is equals to I by 1 plus I. So 1 minus I, yeah. So I into 1 minus I into 1 minus I square. Minus I square is 1, minus 1. So 1 by 2 into I minus I square, that is equals to minus 1. And I plus 1. This will become pi plus 1. B is equals to plus 1. So A is equals to 1 minus B, that is equals to 1 minus 1 by 2 I plus 1, that is equals to 1 by 2 1 minus I think. Yeah, 1 minus half minus half. This is correct. Yeah. So one can check here by replacing this. These terms are correct or not. Just to check this one. So let me check because I was a little confused here. 1 by 2 I plus 1. So this will be 1 by 2. One can take common. This is just to check that 2 1 minus I plus I square plus I square is equals to minus 1 will be cancel out. I cancel out. I cancel out. This will be 0. This is correct. So that means we have to take a is equals to 1 by 2 1 minus I, and b is equals to 1 by 1 by 2 1 plus. So the coordinate vector is actually for this 1 by 2 1 minus I, another is 1 by 2 1 plus I. This is the coordinate vector. So third option is actually correct. 1 minus 2 1 plus I. This is option is correct. Now the last one, 1 plus I plus 1 1 minus 1. So this is what we have to do. So let me do this one. So again we can start from here. So here it will get a plus b is equals to 1 plus I. I'm just separating it, and a plus bi is equals to 1, and b into 1 plus I is equals to minus 1. So what will get, b is equals to minus 1 into 1 minus I by 2. So that will be I minus 1 by 2. So if b is this, then a will be 1 plus I minus 1 by 2, right? Because that is what it is b. So this will be 2 plus 2I minus I plus 1. So this will be 3 plus I by 2. So now let me check whether these are feasible or not. So, A is, this is 3 plus I by 2 plus b is actually I into I minus 1 by 2. This is equals to 2 will be there. 3 plus I plus I square minus I cancel out, but here it is becoming 3 minus 1 2 by 2, that is equals to 1. So that's becoming 1. That's correct. So that option 3 is also correct, I think. Okay, so the thing is that here the vector has to be, what vector has to be, 3 plus I by 2 comma I minus 1 by 2. So let me check whether we have this 3 plus I by 2 I minus 1 by 2. So 3 plus, so this is not matching. So this is not matching. So this is not correct. So correct option is A and C. So okay, any doubt till now, at least in this problem, if you have, you can ask. In fact, previous problem also you can ask. If you have any problem, you can ask. Otherwise, I'm going to the next problem. I hope it's clearly visible. Okay, so I'm going to the next problem. So I hope problem is visible, clearly readable at least, not much small font. Okay. Let V be the vector space over the field of all real numbers of all functions from R into R. Let P1x is equals to 1, P2x equals to e to the power x, P3x equals to e to the power minus x. And Q1x is equals to 1, Q2x equals to cos hyperbolic x. Let me recall you. Cos hyperbolic x is equals to e to the power x plus e to the power minus x by 2. And sine hyperbolic x is equals to e to the power x minus e to the power minus x by 2. Then the matrix P such that this is what it is using. Qj is equals to summation I equals to 1 to 3 Pij Pi. Okay, so here is the matrix is asking Qj. So what it is written? P1 is equals to 1, P2 is equals to e to the power x, P3 is equals to e to the power minus x. Another is that Q1 is equals to 1, Q2 is equals to cos hyperbolic x, Q3 is equals to sine hyperbolic x. So let us take, this is the vector basis of beta, the previous what I have done. This is the basis beta dash. Okay. Now, here it is asked that Qj is equals to summation of Pij, Pi, I equals to 1, 2, 3. Then what is the Pij? Basically basis change. So first case, first one, it's clear that whenever j is equals to 1, so that is becoming 1 comma 1 comma 0. So matrix is, so P is actually 1 comma 0 comma 0. This is clear because if you take Q1, that is 1. So how to write in terms of P1, P2, P3, that is 1 comma 0 comma 0. This is clear. Now if you write Q2, Q2 is actually cos hyperbolic x. Cos hyperbolic x equals to e to the power x plus e to the power minus x by 2. If I want to write in terms of this basis, what will be the coordinate vector? P1 will not contribute anything. P2 will contribute half. P3 will contribute half. That's why this is the matrix. Now if you write Q3, that is sine hyperbolic x, then that is e to the power x minus e to the power minus x by 2. So in that case, how the contribution goes? P1 does not contribute anything, that's why 0. P2 contributes half because, and P3 contributes minus half. This is the matrix P. And that matrix is actually, that one thing I have not proved there, the matrix P, that basis change matrix P from a basis to another basis is actually a unique matrix, unique invertible matrix. I have not said why that is invertible, that also I have not said, because they are basis, so that's why they has to be invertible and they are unique. Those things I have not said, but these are also the part of the statement. So where it is matching, I think this is what it is matching. Yeah, this is what it is matching and no other is matching. Okay, so this is very easy. If you have any, still if you have any problem, you can ask. Otherwise I'm going to the next problem. In fact, after starting the problem you can still ask. There is no problem to asking any problem. Okay, this is another problem. Let W be a subspace of R4 defined as collection of all ABCD such that A plus B is equals to C plus D. So this is very clear that A plus B equals to 0 implies that B has to be minus A, and C plus D is equals to 0, that implies D has to be minus C. So W is actually collection of something like that, A comma minus A, because B is minus B, the B is equals to minus A, C comma minus C. So A and C are free to vary. So this is what it is correctly I have written. Okay. So any vector in W will must look like this way. This is what it is. Now the question, which of the following sets can be considered a basis for W? So now, as I have written, general element is A minus A, C minus C. This is the general element. That can be written 1, A 1 comma minus 1 comma 0 comma 0 plus C 0 comma 0 comma 1 comma minus 1. So this is the what it is one can write. Okay, any arbitrary vector. So basically, if you want to get any vector, you have to take the linear combination of this vector and this vector. This is one way one can get. So that's why one of the bases is 1 comma minus 1 comma 0 and 0 comma 0 comma 1 comma minus 1. So is it matching with someone? Yeah, this is matching with third option, so that's why third option is correct. Let me check with the fourth option. Fourth option is not correct. This is not correct because here A is 1, B is minus 1, C is 1. So if you replace here, C is actually 1 and D is 0, then C plus D does not becomes 0. So that's why the third option is cancelled out. And the first option, the second option, look at second option. A and B is taken in the first place. A and B is placed 1 comma 1 comma 0 comma 0. So A plus B actually 2. That's not becoming 0. Okay. So that's why this is also not correct. But the first option is actually correct. First option is correct. Why the first option is correct? Because you can look at they are linearly independent and they spans the full set. As I have said, if you have something like you have this type of vectors, they spans clearly and they're linearly independent. Let me check. They're linearly independent. So if you want to get any vector also, okay, let me write any vector a comma also a comma minus a comma c comma minus c. This can be written a of 1 comma 1 1 comma minus 1 1 comma minus 1 plus c minus a 0 comma 0 comma 1 comma minus 1. So one can write, you can carefully check that this will be a comma minus a comma minus a, second two term and third term will be 0 0. It is correct. You can check this is very correct. So that implies the set 1 comma minus 1 minus 1 1 comma minus 1 and the vector 0 comma 0 comma 1 comma minus 1 spans W. So now the question is whether they are linearly independent or not. They are indeed they are linearly independent. Why they are linearly independent? You can know that if you want to get some term in the first place, you have to take from here, and if you want to get some terms from the second place, you have to get it. But still, let me show why they are linearly independent. Because this is very easy, so that's why I'm doing, but with not much we have to do. Very simply, one can say this will be x1 comma minus x1 comma minus x1. This is equals to 0. x1 and this will be like x1 plus x2 comma minus of x1 plus x2 and this equals to 0 comma 0 comma 0 comma 0. So you can one will get x1 equals to 0, another will get x1 plus x2 is equals to 0. That says that x2 will be must be minus x1, which is actually 0. So that says that x1 equals to x2 is equals to 0. That says the set 1 minus 1 1 minus 1 comma 0 comma 0 1 minus 1, this is linearly independent. So this spans the set W and this is linearly independent. That is a basis of W. So that's why these two are bases. Basically, this is very simple. Why I'm saying this is very simple. As once I was saying that 1 comma 0 comma 0 comma 0 comma 0 comma 0 0 comma 1 comma 0. Another is 0 comma 0 comma 1. This is basis of R3, right? Also, once I was saying that 1 comma 0 comma 0 1 comma 1 comma 0. Another is 1 comma 1 comma 1. This is also basis. Something like that. Taking summation, first and second and third, something like that, like a b c, you have three vector a b c, you are taking like a comma a plus b comma a plus b plus c. So they are still, if a b c are linearly independent, then this set is also linearly independent. This is generally one can say okay. So let me write, this is something like one can say then exercise, you can check. This is not much very difficult, they're very easy. So let me write as an exercise, if the set alpha 1 alpha 2 alpha 3 are linearly independent, then the set alpha 1 plus alpha 2, alpha 1 plus alpha 2 plus alpha 3 is also linearly independent. First of all, why I am saying this? because here we have encountered something like this. So these two terms are there. If you look at carefully to the first vector, I mean first option, what it is given, it's clearly second vector is as it is given. But the first vector in the first option, they are actually the addition of the, I mean vectors, two vectors in the third option. So that's what I'm saying. Okay. I hope it is clear. If there is any doubt, you can ask. Okay, I'll do one more problem and we'll end here. This will take time. Let me write this one. Yeah, here is a very easy problem. So let me do this. So here is another problem that V is equals to R3 and another box one is the basis. Oh, this is what I'm something like this is what I'm selling that 1 comma 0 comma 0 0 comma 1 comma 0 0 comma 0 comma 1. This is one basis. Another basis is that 1 comma 1 comma 1 1 comma 0 comma minus 1 0 comma 1 comma 1 with another order basis. So let the matrix xyz in terms of w1 that is x1 that is basically x comma y comma that implies that x1 is equals to x comma y comma z. This is the vector, right? Because this is the basis and this is the vector x comma y comma z. So with respect to the first basis, this will be the coordinate vector, and with respect to second basis, what will be the coordinate vector? Okay, then the matrix P such that this holds. So here we have to find the matrix P, basis change matrix basically, from this basis to this basis. So the same thing, we have to try to write this basis in terms of the first basis and we will get the matrix. So here beta is equals to 1 comma 0 comma 0. This is first 0 comma 1 comma 0 0 comma 0 comma 1. This is another basis. This is one basis what I'll call alpha 1, alpha 2, alpha 3, and beta dash is equals to 1 comma 1 comma 1 comma 1, sorry, this is 1 comma 0 comma minus 1 comma 0 comma 1 comma 1. This is another. So let me write it as alpha 1 dash, alpha 2 dash, alpha 3 dash. So the matrix, basis change matrix is actually from beta to beta dash, that is P. So P is actually the basis change matrix from beta to beta dash. So for that, what I have to write, alpha 1 dash is actually you have to write this in terms of alpha 1, alpha 2, alpha 3. That is alpha 1 plus alpha 2 plus alpha 3 clearly, because if you want to write 1 1 1, you have to write sum, you have to take sum of all of them. This is what it is. So that means P matrix, the first column is 1 comma 1 comma 1. If you write alpha 2 dash, that is equals to 1 comma 0 comma minus 1, what I will get, you will get alpha 1 minus alpha 3. That's clear, very much easy. So 1 comma 0 comma minus 1. And if you want to get alpha 3 dash, that is equals to alpha 3 dash, that is equals to 0 comma 1 comma 1. How will get that will be like alpha 2 plus alpha 3. So this will be like 0 1 comma 1. This is very easy actually. 1 1 1 1 0 minus 1 is the first option, is the correct option. And as I have said, there is a theorem. This will prove that this is unique. So this is unique. So that's why the other options are not correct, because basis change matrix here it is asking. Okay. So let me write one more problem then, because I have time. We have to fill the time basically. This is what we have done. Yeah, this is the only problem left. Whatever. Okay. This is another problem. Let V equals to R3 and W is equals to, this is a basis. This is a basis, be an ordered basis. The coordinate of 3 to 1 with respect to denoted by 3 2 is what it is. This is what it is asked. So now one can start. So basically what will be the coordinate will be like x1 x2 x3. So basically this will be 2 1 0 1 minus 1 1 0 0 1. This is with what is the x1 x2 x3 such that we will get 3 2 1. Am I written correctly? No, I think just a minute. No, I have written not correctly. No, this is correct. No, not correct, not correct. Let me x1 basically what I have to write. Let me clearly mention clearly what I have to. So basically what I have to do that x1 2 comma 1 comma 0 plus x2 1 comma minus 1 comma 1 plus x3 uh, x3 0 comma 0 comma 1, that has to be equals to 3 2 1. Okay, so that means 2 1 0 2 1 0, this is what will be the first equation equals to 3. Second equation is x1 x2 is 1 minus 1 x3 is equals to 0. This is the second equation. Third equation is 0 1 1. This is the matrix. So let me check x1 x2 x3. This is equals to 3 2 1. This is what we have to get, right? Like first column, second column, third column. Yeah, this is correct. So now how to do this type of problem? Let me, as we have very short time, I will first discuss how to do this type of problem. So how to do? You have to find x1 x2 x3. So what we have to do? We have to consider 2 1 0. We have to row reduce this process, but here we can't interchange a row. We can interchange, but anyway, you have to solve x1 x2 x3. You can do many ways, but I want to just do the standard method. If you want to go through the standard method, what will be the standard method? Standard method will be like um, you have to do the row reduction process with this. You have to do the row reduction process. Yeah, you have to do the row reduction process, but you should not change the. This is the matrix. So if you do the first row reduction process, you have to take, this is the augmented matrix called augmented matrix. So first will be, you have to make 1 here, so that 0, that will be 3 by 2, then it will be as it is 2 0 1 1 1. So now what you have to do, that we have to make this term 0. So how to make that? R2 dash is equals to R2 minus R1 will be 1 half 0 3 by 2 by minus 0 minus 1 minus half minus 3 by 2 0 2 minus 3 by 2, that is 1 by 2. This is correct. 0 1 1 1. So now what you have to do, you have to make this term. You can do many things, as these are the all. You have to make this term. Also, this is enough. I think this is enough. So this reduces that x1 plus 1 by 2 x2 is equals to 3 by 2. Second equation is actually 3 by 2 x2 is equals to 1 by 2, and x2 plus x3 is equals to 1. So this will give x2 is equals to minus 3. This will give x3 is equals to 1 minus x2, that is equals to 4, and this will give, why everything coming in terms of, no, there is some mistake. I think there is some mistake. Row reduction process, if I do, I have to multiply half. I have done that. After that, I have to make 0 here. If how to minus 1 minus half 0 2 minus 3 by 2 4 by 3, that 1 by 2, that's correct. And last one will be as it is, that's correct. So x1 plus 1 by 2 x2 plus is equals to 3 by 2, that's correct. Minus 3 by 2 x2 is equals to half, that's correct. X2 plus x3 is equals to 1, that's correct. Okay, let me write clearly. Let me go to the another way, that is like 2x1 plus x2 plus x3, this is equals to 3, and x1 minus x2 is equals to 2. Another is that x2 plus x3 is equals to 1. So from these two comparing, what we'll get, they'll get, if I compare x2, what will get? Ah, here is the one thing, right? 2x1 plus 1 is equals to 3. So x1 will be 3 minus 1 to 1, right? So basically x1 is 1. So that means from here, this equation, what I'll get, x2 is equals to x1 minus 2, that is equals to 1 minus 2, that is equals to minus 1. And x2 is equals to minus 1. So x3 is equals to 1 minus x2, that is equals to 2. Yeah. So 1 minus 1, 2. But I don't know what option is given. This is not correct options. Okay, let me try read the questions once again. This is an order basis of then the coordinate vector of this with respect to this denoted by this is what it is. 2 1 0 1 minus 1. This is correct. There is some problem. I have to check this one, but the correct option is this one. This x1 is 1, x2 is equals to minus 1. So correct option is 1 minus 1 2. This is the correct option. I believe there is some problem with this. I'll check once. I hope this is correct. Okay, so if you have any other problem, you can ask. Otherwise, I'll end this today's class in next 1 minute, and we'll meet in the possibly next Saturday. And if there is any change, there will be a mail. And there is one possible change will be there. Let me tell you, there will possibly change will be there. One Saturday may reschedule to the only Monday. Otherwise, every classes will be on the Saturday. Only one Saturday can reschedule, possibly. But that will inform you. Thank you. Questions pattern, yeah. In general, there will be most of them MCQ, but I have to ask to the faculty. I think they will inform you. Not a problem. And that maybe not all MCQ, but you know that the exam will be on the offline basis. Okay, that is not online basis. So MCQ or not, that doesn't matter. Okay, so if you have any other problem, you can ask. Otherwise, in few seconds.